Welcome back to a new video. In this video we will discuss the frequency response of a MOSFET amplifier. This will be a very interesting example where we see a MOSFET amplifier and the three capacitors and the effect of it on our amplifier in the frequency response. Of course, we will see everything step by step in our calculations and verify these in SPICE simulations. Okay, we have the following circuit given. We have the MOSFET M1 here. The parameters for our MOSFET are shown here. Threshold voltage 2 volts. The process parameter K sub n is here 5 milliamps per square volts. And the lambda is 0, so we will not have any channel length modulation. There are capacitors C1, C2 and CS. C1 and C2 are 1 micro and 1 microfarads, and CS is 10 microfarads. The circuit is powered by one DC voltage source, 18 volts VDD, and the resistors are shown here in the values. What you want is the following. We like to determine the transfer function in the Laplace domain, so the VO over VI. We also want to know what the maximum voltage gain is for this specific circuit, and we would like to know the cutoff frequency, in this case the lower cutoff frequency. So let's see how we can deal with these unknowns, the questions for this circuit. Okay, let's first start with the small signal circuit, but then for specific the frequency analysis. Now this is the circuit we can use. This is the small signal circuit. You also see in addition the capacitor C1, the C2 and the CS. Those are the coupling capacitors C1 and C2, and this is the bypass capacitor CS. In order to determine this transfer function, VO over VI, we separate our problem in three different parts. So we will make it actually in sections. How I do that? I will make actually the transfer function in three fractions multiplied by together. So we have now the VG over VI, and that VG is this node, which is the gate voltage. And then times the VGS, this voltage, divided by the voltage at this node to the ground. And the final one is the output voltage, VO here, divided by the VGS. And if you look at it, VG will cancel, VGS will cancel, and you end up to VO over VI, which is exactly as we have it in the original form. And why is this more convenient? This is easier to determine, these three parts, than going directly to this transfer function. That's why we do it. So first, the part VG over VI, that is effectively going from the input to this node VG, voltage divider rule actually. So you start at the input and you look at this node. Since this is an open, you can actually see this disconnected from the other part of the circuit. So you can say these two resistors in parallel divided by the complete resistor or impedance seen by the VI. And that is actually shown here, the RG again. I will define that as the two resistors, parallel R1 and R2. That's given by this expression. So I will have VG over VI, which is then RG, divided by RG plus RI, and also 1 over the SC1, which is our reactance of this capacitor. Now we can write this in a more convenient way. Multiply the numerator and denominator by SC1. That's shown here. And we can also take out the RG out of this part, and also the RG and RI also. So we get a fraction which is just a constant. We also divide by the C1. That's the numerator and also the denominator. So you get actually this part where you see here the 0 at the origin, and there is a pole at 1 over C1 times the summation of the RG and the RI. All right. Now we will express the next one, which is the VGS over VG. That's the expression going from the gate to source voltage and divided by the gate node voltage. So that's actually the part here. I will define this source node voltage, which is important for the next steps. And I also say VG voltage is equal to VGS plus VS, which is effectively our current, the voltage law of Kirchhoff, so Kirchhoff's voltage law. Then I can say the following. What is now this expression? Well, we can now apply here the Kirchhoff's current law at this node source by saying this VGS is equal to the current through the resistor plus current through the capacitor. And we apply, of course, everything in the Laplace domain. So the capital letters meaning actually not DC, but the Laplace parameter. So we have a GM, VGS, is equal to Vs, this voltage here in the Laplace, divided by the reactance of this capacitor CS, and also the same voltage divided by the resistor Rs. Now we can now say the Vs over 1 over SCS is effectively actually this CSC times Vs and then plus this. And we can now take this together, so we can say SCS plus 1 over RC in the parentheses times Vs. That's actually shown here. Of course, we want to go to the VGS over VG. I already see some expression I can use in this expression, so I would like to have an expression for Vs. That's this one. So what I do is the following. I will do the left side divided by this part in front of the Vs. That's now the expression I can use in here. Because this expression has only VGS, which is also what you see here. So if I apply this in the Laplace domain, so I can say Vg is equal to VGS plus Vs actually, which is from here. Then I have everything here in the VGS and the VG. Now I will take this out of the parentheses, so I will have here 1 plus Gm over SCS plus 1 over RC, and then times VGS, of course. And if I now do VGS over VG, that will be then actually in 2 steps, 1 over that fraction I just described, so 1 plus the Gm over SCS plus 1 over RC. Again, to write this in a more convenient way, I can multiply the numerator and denominator by this, so that just C SC plus 1 over RC. And again, you can continue by multiplying also everything here, numerator and denominator by RC, or I mean RS. That's what you see here. And you can continue by also making this in a form or setting this in a form where you see the 0 in the pole directly, which is actually shown here. So you divide by the RSCS, that's this part. And you also do that here. So this constant will be divided by the RS and CS. Well, what we want, for example, this is a form, what is standard form, which where you have 1 over the resistor and the capacitor. And this is not really the form where you actually see the 1 over the resistor and the capacitor. So you can do that by looking at this expression and then write it down in this form. So you can say 1 over CS and then times the impedance, which is actually the parallel combination of 1 over Gm and the RS. So we have now this part given here in the blue region. That is actually this part encircled in blue. And we have also the encircled in red. That is actually what we have done here as the second step. Okay, let's take this here together and now do this final part, which is V over VGS. So that's the expression of the output voltage in terms of gate to source voltage. So how about that? That is the question now here. Well, what we can say is the output voltage here is, using Ohm's law, the current through the resistor times the resistor RL. And what is this resistor here? And what is this current here? The load current. That current is the same as the current through this capacitor C2, and we actually see here this branch, another branch here, and that is supplied by this current, which is the GM-VGS. So we can actually say, again, using Ohm's law in Laplace domain, of course, and then use the current divider rule at this drain node. So we can say the following. This current IL is equal to minus GM-VGS. Why minus? Because this is going in this direction, while you are actually looking in this direction with your current, which is in the other resistor, which is RD, times the summation of the resistors in the two branches, which are the RD, RL, and 1 over the SC2, which is our reactance of the capacitor C2. Again, we can write this in a more convenient way by multiplying the numerator and denominator by SC2. That's what you see here. And this expression is now the current here for the load. And that can be now multiplied by the RL. And that's shown here. So what you get is this RL in the numerator. And now you have an expression which you can use. That is the ratio here, V over VGS, by dividing actually the left and right hand side by the VGS. And of course, everything in the Laplace parameters. And that is actually a more convenient way to work towards the final result. What we then do, we will now take out the constants and also evaluate that such that you see the 0 in the pole clearly. So we take out the RD and RL as a product out of it, and also the RD and RL as a summation. That's what you see here. And then you divide by also the C2, and that is in total shown here. So this part, which is now given in the encircled pink color, that is the final part here. Okay, now taking this together here and then looking at the complete expression, which is the product of these three parts, then you have this large expression for the complete transfer function for this voltage gain VO or VI. Again, we can recognize, of course, here some constants so we can make it more convenient. And again, this is the blue, the red, and the pink part here. Now what we can do, we can take this RG and the RG over RI in front, and also this minus GM and the parallel combination of the RD and RL, because those are all constants, and the other are the dynamic parts of the circuit. So this is the part where you see here as a constant, and you see here S, another S, so it will be an S squared, so 2 zeros actually at the origin, and we have another zero here at this part, and we have 3 poles, one of them here, which is actually shown here. The other one is here, that's the second pole, and the third pole here. So it's actually more convenient to see this in this format, so you see the product of the zeros and the product of the poles as shown here. All right, let's bring them here and continue with the next part, which is our maximum voltage gain. Before we do that, let's also designate the zeros. As said before, we have the zero, omega Z1, which is 0, but omega Z2, which is the second zero, is also at the origin. And the third zero is 1 over the RSCS. So that will be determined by actually this resistor and this capacitor. And the poles are determined by these 3 parts, which is then given here omega P1, 1 over this actually expression, and then this expression and this expression, omega P2 and omega P3. So how about then the maximum voltage, the voltage gain? Well, that happens in this case if you look at the expression in the limit, this S, if that is going to very large values, so to higher frequencies, because this is a high pass filter expression, then this complete expression here is then almost S to the power 3, because that will be dominating. That's also counting here, so you get actually S to the power 3 divided by S to the power 3, so it's almost a unity here. And then you only have left this expression, which is our maximum gain. And that's what you see here. So the maximum gain you can get is this part, which is also shown here. Now the lower cutoff frequency can be calculated, because that was the next part, the final part, can be calculated using this approximate expression, where you see here the square root of the summation of the poles squared each, and then minus the 2 times the summation of the zeros squared. So you start with the poles and you might do minus to 2 times the summation of the squared of the zeros. So let's do that in more detailed form. So this is the omega L, which is then the lower cutoff frequency, is then the square root of square this omega P1 plus omega P2 squared plus omega P3 squared, take it in parentheses, minus 2 times omega Z1 squared, omega Z2 squared, omega Z3 squared. That's actually shown here. So if you know these, you have a nice approximate value for your lower cutoff frequency. Okay. Now let's see that in more detail, of course. For that, we need to do the DC analysis first. And now we assume for our transistor M1 that this is operating in the saturation region. That means actually the following: the VGS, which is this gate to source voltage, is larger or equal to the threshold, in this case 2 volts. And we also assume that this drain to source voltage is larger or equal to the gate to source minus the threshold. So we need to check this, of course, later. So we assume first and we will check later if this is indeed correct. And now if this is a saturation region, we can also apply this or use this formula, which is the drain current formula. This current, also this source current, is equal to Kn, given here, times the square of this VGS minus V threshold. Then we can bring our DC circuit here. You see here the circuit we can use for our DC analysis. The capacitor C1 and the capacitor C2 will be open, so we will actually lose this part and this part of the circuit, and the CS will be also open. So in DC, everything for the capacitor will be an open circuit, so you actually get this middle part, and that's actually also shown here. You see the drain current, the source current, they are exact same equal to each other, since the gate current is 0. And I will use here, I will designate here the gate node, and I will calculate here the gate node using voltage divider rule. Why can I do that? Because the gate current is 0, so I can assume this as one branch. I cannot do that if I had here a BJT, because there will be some base current flowing here, even though it is small, so I cannot use that. So I need to use then the Thevenin equivalent circuit to continue. Okay, so continue with the voltage at node G using the voltage divider rule. So there will be then R2 over R1 plus R2 times the VDD. So you substitute here the 500 kilo ohms given here and divided by the 600 kilo ohms plus 500 kilo ohms times the 18 for the VDD, and that will result in 8.182 volts. We can now apply here in this branch, this part, this loop, the Kirchhoff's voltage law. And I say Vg is equal to Vgs plus the voltage across the Rs, which is actually shown here. Since Is is also equal to Id, I can use that in this case, so I can say the drain current is then given by this expression, which is also equal to the Is. So taking this together, so I actually substitute this expression here in here. So we have now here an expression where you see the Vgs as the only unknown, because the Vg is calculated. We know the Rs, we know the Kn given here for the MOSFET, and we also know the threshold. So everything is known here. So let's substitute that. So we see here the 630, because that's Rs. We also have the Kn, which is 0.005, which is 5 milliamps per square volts, and the threshold voltage for the MOSFET is 2 volts. Now continue, so you multiply these two, and that will be the 3.15. Now you can solve this using a solver. That will result in two solutions. One of them is 0.4314 volts, and the other one is 3.251 volts. Which one is now valid? Now this one is less than the threshold voltage of 2 volts, and this is larger than the threshold voltage of 2 volts. And we assumed the saturation region, and that was necessary in order to continue in this case for using this formula. But for that we need to fulfill these two conditions. So VGS must be at least V threshold. In this case it's not valid, so it is now in this case valid. So the valid solution for this case is 3.251 volts. That's also what we will use for the next calculations, and also for the drain current. So for the drain current I will use this formula using the VGS of 3.251, and if I do that I will get here 7.827 milliamps. What we also can do, because since we know the drain current, we also know the source current, we can check this VDS in order to check this second condition for the assumption of the saturation region for this MOSFET. So we can apply here again Kirchhoff's voltage law going from top to ground. So we say VDD is equal to this voltage across the RD plus the VDS plus the voltage across RS. That's actually shown here. We can now group these two resistors, RD and RS, because they have the same current, and then call it times RID or IS, it doesn't matter. And now calculate the VDS here, that's actually shown here. So 18 minus actually this, which is 1000 plus the 630 times the current we just calculated. And that will be 5.243 volts. Is this according to this condition? Let's check that. This should be larger than the VGS minus the threshold, which is then 3.251 minus 2, which is then 1.251, which is definitely, this one is definitely larger than that one. This is the limit, so we are way above that. So we can say this is also valid, and we have now proven that our assumption is correct for this MOSFET. All right, and we can now continue with the parameter GM we will need for our gain, but also for our lower cutoff frequency next steps. And GM can be calculated using this formula, which is then 2 times the square root of the product of the drain current, DC, times the Kn, which is given for the MOSFET. Now we know the drain current from here, and we also know this Kn from the MOSFET. That will result in 12.51 millisiemens. All right. Let's continue and now go to the AC analysis. Now we have the GM, and for the maximum voltage gain we know that this formula was valid, so we have here the GM we actually require, so this is just calculated in the final step in the DC analysis. So we can now substitute here the values. We know the RG here, which is the parallel combination of the R1 and R2. Now let's calculate that, which is then 600 kilo ohms times the 500 kilo ohms. So there's a parallel combination of these two resistors, and that will end up to 272.7 kilo ohms approximately. So we will substitute here everything. You see that RG, RG, RI. RI is 100 ohm. So this is approximately 1 actually. And we have now here the GM. And you have also a minus, so it will be of course an inverting amplifier. And that will result in minus 10 very close to -10, it will be then in the dBs. 20 log of that absolute value will be then 20 dB. All right. Okay, next step is the lower cutoff frequency. Now we need for that the zeros. So we already know that we have 2 zeros at the origin, and the third zero, for that we need to have the resistor RS and the CS. So we have here, this is 10 microfarads, so 10 to the power -5 effectively. And that is then equal to 158.73 approximately radians per second. Now for the poles, we have these three expressions. You see here the GM, so that's why we need to do that in the DC analysis. So we substitute here the GM and also the resistors we need. You see here 3.6653 radians per second for the pole 1. For the pole 2, you see here 1400 9.9 radians per second, which is much larger than the first pole. And this is exactly 200 radians per second. So you see actually here that the third pole here, or I mean the second pole, is the dominating pole in these poles. And now we can say the lower cutoff frequency using the formula, the approximate formula we have described. So we actually take the square of each pole, add them up, and then do minus 2 times the square of each zero, add them up. That's actually what you see here. So you see that actually here in more detail. So everything is actually here squared, and then minus 2 times the each squared of the zeros, and that will end up to 406.1 radians per second. Interestingly, this is almost actually this. So if you just assume that this will do the job, or it's a nice approximation, is also very handy to know that if you have a very large pole in your system. And if you now convert this to hertz, just using the omega L over 2 pi, that will be then 223.8 hertz. So we have now done the necessary calculations. So let's now continue and look in the simulation results and check our calculations. First, we start with DC analysis. This is the DC analysis circuit. You see here the nodes, and this is the table I will bring up. And what you see here also are calculations, the VGS, ID, and the VG. VG is actually shown here, which is then the 0.1 in the simulation. So it's just 8.182 volts, which is exactly as we have it. So this is nice. And the drain current is the current through the RD. That's this one, which is 7.827 milliamps, also exactly as we have it. Now the VGS can be calculated as the voltage at node 1 minus the voltage at node 3. So we need to take that and that one. Now if you calculate it for yourself, this will be exactly actually this one. And for the VDS, you need to use the voltage at node 6, which is this 10.173, minus the voltage at node 3. Again, if you do that, you will get to this value. So they are all verified. All right, the important part here for our discussion is, of course, the Bode plot, where you see the gain, but also the lower cutoff frequency. So you see here the Bode plot. For the gain, you see indeed there's a high pass filter characteristic. So it is actually starting very low and then coming up, and then levels to a voltage gain here. And this is the circuit we, of course, used. So what do you see? Now we have calculated using the values we have determined and also given. The -10 is the gain, voltage gain, which is then 20 dB. And if you see that here in the simulation, it's also exactly 20 dB. So this is a very nice result. The lower cutoff frequency we had calculated was 223.8 hertz. And we have here 225.8 hertz. So it is a small error, just 3 hertz lower in our calculation than the measurement. So I mean the calculations. So this is not really a big deal. Of course, we also made some approximations and also some rounding off errors. So this is a very nice result. So we can say we have actually achieved our goal. All right, it was our example considering the frequency response of the MOSFET amplifier having 3 capacitors. So 2 coupling and 1 bypass capacitor. And we have worked out the frequency analysis in the small signal model and also done the DC analysis to calculate the necessary calculations for our maximum voltage gain and the lower cutoff frequency. If you have any questions, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.